Hello, ladies and gents. Once again, I appreciate your flexibility today as we investigate the volume of three-dimensional solids with known cross sections. I know not necessarily the ideal scenario to do this kind of virtually, but we're going to go ahead and see if we can figure this thing out. So what we have here is I have the graph showing of the square root of x and then x squared, right? And we're looking at really this space in between here from 0 to 1. And you can see pretty easily they intersect there at the point 1, 1. They intersect here at 0, 0. And those points are going to be important to us. So what we're going to consider is instead of taking this region and rotating it, say, about the x-axis or the y-axis or some other horizontal or vertical line in space, we're going to actually consider that it now cross sections or this three-dimensional shape is sort of going to grow off of the screen or grow off of the board if you were on the board. And we're going to have cross sections that are told to us. The shape is told to us. And these cross sections are either going to sit in here perpendicular to the x-axis or perpendicular to the y-axis. So let me show you what I mean. Get rid of the curves and just kind of zoom out. Oh, maybe not that much. I'm just going to move this over to the side so we have some room to work. Let's see if we can get this going. Okay. So let's say that we're starting this problem out and we're going to go with squares. Our cross sections are squares and they're going to be perpendicular, right? International sign for perpendicular to the x-axis. And they're going to sit in this region from 0, 0 to 1, 1. So the base of these squares is going to sit in here. And these squares are going to grow off the board. So from like a three-dimensional standpoint, they'd almost sort of like come out here and here, and they'd sit, and there'd be one of the bigger square cross sections would kind of be here in the middle, whereas down here there'd be kind of like this littler version of a square, and you're kind of three-dimensionally angled there. If you want to look at another visualization here, go back to my pointer tool. This is a nice website, and I'll put the link out there for you to kind of see what happens here. So here's on the left, you can see the graph, and this is just like here on the left, you can see the graph, and this is just like what we have on the Desmos screen. And I'm going to click squares, and we're going to have perpendicular squares, perpendicular to the x-axis, that is. And you can see I'm like kind of moving this square along, and you can see how these squares are sort of down here and really small. And then as they move through three-dimensional space, they get bigger and bigger and bigger, and then smaller and smaller and smaller at the top end. But it's not just one square that we're getting here. We're getting this whole three-dimensional solid. And it starts down here. And if I raise this up all the way, I'm making 100 cross sections here is what I'm doing. And I bring this up. This shape is really the shape that's formed in this three-dimensional space, right? If you were to put this on a slicer and take one little slice out of this three-dimensional figure, it would be a square. And you can kind of see that cross section there. But this shape then fills in with all these squares all the way through, right? They fill in all through the shape. So we want to find the volume of this, right? We want to see what the volume of this shape is going to be. And again, we're given these graphs, we're given x squared, we're given root x, and then we're given the cross sections are perpendicular to the x-axis, and they are squares. So let's go back to our sheet here. And what do we want? Well, how can we do this? Well, if you remember, and I'm going to kind of write on here and then erase things and start over again, but if you remember back to when we did volume with disk and washer method, what was that really? Well, when we did disk method, it was pi times the integral from a to b of a radius squared, and then it was usually times dx or maybe dy. And what that really was we had some cross section. If we took some space and rotated it around, right? We started out with like this space and we rotated around the x-axis and we had like this cross section. The cross section that was in here was this really, really thin cylinder. The height of this cylinder was this little, we said it was a dx height as we took that down to almost nothing. But then the area of this cross section being a circle that area was pi times radius squared. So the volume of one of those cylinders, the volume of that really, really thin cylinder kicked on its side, was pi r squared times dx. And we summed those from the beginning to the end, from A to B. So kind of a crude definition of what that sort of looks like and where that came from. And then when we went to Washer method, we just got two involved, right? And threw them together in the same integral expression. So now we're going to use the fact that we could do this, that if we know the infinitely thin height of one of these cross sections and we know the area formula for the cross section, we could change the cross section and still find the volume. Let's erase this and I'll show you what I mean. So in the example we have here, we have root x on top and we have x squared below. And our cross sections are squares. So if we know the area formula for a square, we can find the volume for this guy. The volume for this guy is going to be simply the integral from a to b of our side squared dx. Why will it be side squared? Because that's the area formula for a square, and when we multiply that by that dx thin width, that gets the volume of one square. And if we sum those squares from beginning to end, from, in this case, 0 to 1, so let's put those in here, right? From 0 to 1, those are our x limits of integration because we're integrating with respect to x. We can figure out what the volume of this guy would be. Well, so what would our side squared be, right? Like this is our side that we want to put in here. So what would this side be? I'm not feeling that E. Let's try that again. So this side is really whatever that distance is. But we just got done with disc and washer. We know how to find that length. I think that that would just be the square root of x minus x squared. And the square root of x minus x squared is literally that length. And it's that length anywhere along here. If you tested that, if you put in any value between 0 and 1/2, root x minus x squared would literally give you that distance anywhere along the way. In fact, it would even give you the distance at 0 and at 1, right? It would be 0 minus 0 and 1 minus 1. So now that you have this, it's just a matter of figuring out what the actual answer would be, right? Now, this is not a particularly ridiculously difficult integral to do. You're not really going to use sub this. You would probably need to take this guy and kind of FOIL him, multiply him out, use your rectangle if you want to, and then add one, divide, put in 1, put in 0. You might be given a problem here where you have to set up but do not evaluate a function. In which case, here's your an expression. So here's your integral expression that would represent the volume. Or you may be given a calculator, and then you could put this into the calculator the same way you've been doing with some of your practice with disc and washer method. Right? So that square is perpendicular to the x-axis in this sort of setup. But what if we change the shape? Because if we can do it with squares, we could really kind of do it with any shape that they give us. We know the limits of integration. As long as we know what the shape is and when it's perpendicular to the x-axis or y-axis, we can kind of figure this guy out. So what if they changed the shape, and what if they made them the cross sections semicircles? Right. So your base is still in here, and it's kind of diagonal. It shouldn't be. It should sort of be horizontal. Or vertical, perpendicular to the x-axis, right? And you have these semicircles coming out of here. Right. What would this look like? Well, first of all, I'm going to clear this for a second so that we can pop in here and look at what happens when I'll dial this back. Oh, come on, give me my clicker. There you go. I'll dial n back down to 1, so we just see one cross section. And we'll put it right in the middle. And now let's get semicircles. And get rid of our squares. So now what does this look like? Right, as we take this and build this up and we get more and more cross sections. Well, here's kind of the solid shape, and you can see how this sort of grows off of the graph, right, in 3 dimensions. And there's smaller circles at the endpoint because, well, the diameter is smaller at the endpoint than there would be in the middle, because in the middle you have a bigger diameter, so there's where your biggest cross sections would be. And so now we're looking at the volume of this solid shape, right, with an infinite amount of half circle, semicircle cross sections in that finite space from 0 to 1. So let's go to work. If we have, again, cross sections that are semicircles, right, in here, how can we find the volume of this? Well, my volume is going to equal the integral from beginning to end from 0 to 1. Remember, we're perpendicular to the x-axis, so we have this little thin dx width of each of these. So we're going to integrate with respect to x. I'll throw that out there. And I know the area of a circle is pi r squared. But in this case, it's really pi halves r squared. That would be the area of one cross section. So I'm going to be smart about this. I know that pi over 2 is a constant multiple, so I'll pull that out front. And the rest of this is just something square. Now, this is where everybody has a tough time. And this is where every year we see people mess this part up. They want to go in here and say, like, oh, okay, this is cool. I know exactly what this base would be. Right? This base is just the square root of x minus x squared. It's the same thing as my square. It's just that base across. But be careful. If this is a half circle, what does that base really represent? That base is really the diameter. What I really am looking for is half of that base. I'm really looking for the radius. What I need to do is instead make sure that I take that full base, which we said was root x minus x squared, and divide that by 2. And make sure that that's all in that parentheses and that all accounts for the radius. I can evaluate this integral either with a calculator or by hand the same way I did before. My first step in evaluating this integral, and I'm not going to go through all the steps here today. You'll have plenty of practice with these, but I might make this pi halves times the integral from 0 to 1 of 1/4 times root x minus x squared dx. And then I'd probably bring this 1/4 out front and make that pi over 8. And then, sorry, I forgot my squared. And then continue from there with my multiplying out, my add 1 divide. And if I didn't have a calculator, I'd go from there to find the volume of this with semicircles. We'll practice this with squares. We'll practice this with semicircles. We'll practice it with triangles, and we'll practice it with rectangles of a known height or a constant height. And we'll see all sorts of different examples there. So let's clear this. Let's see if we can get ourselves one more example. So you'll see I have graphs here of sine x and cosine x from 0 to 2 pi. And what we're going to do is we're going to see if we can find the volume of some different versions of these things. Again, we're going to go perpendicular to the x-axis, and we're going to keep them in between the first two intersection points. So in between here and here on this graph. So I'm going to get rid of my functions there. I'm also going to now, my dots are off, so I got to clear this guy. And we're going to zoom out here so we can see it, but it's not completely in our way. All right. Oh no. Hold on. Touchscreen difficulties here. Okay, we're back. Here we go. So let's start out with, let's do rectangles this time. All right, let's do rectangles with a constant height of 3. And again, we'll make these perpendicular to the x-axis. So what does this look like? Well, now I have these rectangles that start out in here, right here, like the bases of these rectangles. And for these problems, just as a side note, I love to look at a sketch of these things. I love to draw a couple different bases in so I can kind of get a feel for this. I have some really big bases here in the middle, but some really tiny bases at this end and at this end. So I know I'm going to have to find that base, and the height is 3 units. So this is kind of like a really short but tall sort of looking thing, because no matter what the bases are, my height is constant 3. So it's like some sort of flat top, right? If this is coming up 3 units out of here, and this is coming up the same amount, even though my base is really skinny here and a little bit longer here. Right, we're still rising up 3 units. So there would be just a very skinny sort of like singular point here, as this curved back, creating a really kind of funky three-dimensional shape. So how could we find the volume of this? Well, again, we have a very thin dx width, and all we have to do is find the area of one of our cross sections. So the volume is going to be equal to the integral, and we need a beginning and an end, so we need a point of intersection here and here. I'm thinking pi fourths for the beginning. That's where sine equals cosine. And I know that this sine curve is at pi here, that cosine is at pi down there, -1. And I know that this point is using the kind of symmetry of this. If this original intersection point is at pi fourths, where pi fourths past pi, that would be 5 pi fourths. And what would the area of my rectangle be? Well, it would be the base times the height. The height's 3 times my base, my top curve, sine x, my bottom curve, cosine x. How about sine x minus cosine x dx? And you might be thinking to yourself, but Mr. Lewis, what happened to the square? We had squared in the first problem, we had squared in the second problem. Like, where's my, don't have to square the base? Well, no, the squared came from the fact that the squares were side squared. That was the area formula for a square. For a semicircle, it was pi over 2 times a radius squared. This one, it's 3, the height, right? My height's 3 times the base. So my formula is 3 times the base. My base was sine minus cosine. If I were to do squares, if I were to change this whole problem and make it squares, it would just be sine x minus cosine x squared. Maybe I were to change this and say, we're going to make rectangles, and instead we'll use a different color, switch on to blue. We're going to make heights, instead of being 3, my height is going to be equal to, we'll cross that out with height, where the height is 2 times the base. So my rectangle is twice as tall as it is wide. How could we figure this out? Well, the area for this new rectangle, the area would be the base times the height, which is just 2 times the base. So my area is really 2 base squared. How does that translate into a volume? Well, how about volume equals the integral? Again, we need x limits of integration because we're integrating with respect to x. And let's see here, I need 2 base squared. So 2 I'll pull out front because it's a constant multiple, times the base, which we know is sine x minus cosine x squared dx. And there's my volume integral, right? It's just whatever that cross section is, you just need to find the area of that. Some people think I'm crazy. Well, you could do some crazy shapes with this thing, right? You could say that you're really going to create a new shape, and your new shape is called a whatchamadoo, and an area of a whatchamadoo is 3e to the root x times pi over x squared. And that's the area formula for a whatchamadoo. X is going to be the base, right? So maybe we want to change this, and we'll say it's, as long as I know the base, right, distance for my whatchamadoo. My whatchamadoo looks like this. It goes around, has a base, and then it goes back down here, and this is down here. That's my base. And this is a whatchamadoo, and it's a new shape that I've just made up. We'll close it up here. And you get the idea. And these things are growing out of here. So the bases are sitting in here, and they're once again, my whatchamadoos are perpendicular to the x-axis. So what's the volume of my three-dimensional shape with cross sections that are my new whatchamadoo shape, right? We'll even color this guy in here, make it fancy. Well, because I know the area formula for my new whatchamadoo shape, I can say the volume is the integral from the beginning, pi fourths, to 5 pi fourths, of my area formula, dx. What's my area formula? Well, it was e to the square root of the base, which I know is sine x minus cosine x, right, times pi over my base, which was sine x minus cosine x, all squared. So it didn't even matter that this is some fictitious made up shape because I had the area formula for one of these things and I knew what the base was, right? And where that sat. And I was able to set up a volume expression, integral expression for this guy. So I hope that that helps you kind of figure all this out. I hope that that's a good kind of crash course in cross sections where we're able to do different shapes. Again, I'll put the link to this 3D visualizer here from GeoGebra. Not loading now, but I'll put that onto your links for today. Check these out. Your work now that you've kind of gone through a couple of these examples is to try some of these on your own. You have a couple to try in Delta Math. I think we have to get up to 3 right here, and that's your classwork for the rest of the day. And if you don't finish, your homework to do tonight for tomorrow. So thanks again for your flexibility today, and hopefully I'll see everybody tomorrow.